So hello, today we're going to start chapter 26, which actually puts us at the halfway point now that I think about it. Because, yeah, this is the 6th chapter. So, halfway through the class, that's cool. Well, I guess when we finish this chapter, we'll be halfway through the class, right? 20, 21, 22, 23, 24, 25. No, we're at the halfway point. This is at now, right, the halfway point. So, halfway in. And we are going to talk about light. At the very end of 25, we introduced the electromagnetic spectrum. We started talking about light, but now we're really going to get into it. And we're going to talk about ways to kind of mess around with light, aka reflection and refraction. This chapter and the next one kind of work in tandem, where this one's just going to be the physics behind reflection and refraction, where the next one is going to be ways to use it, aka mirrors and lenses. But for now, let's just talk about light. So around 1000 AD, people said, okay, you know what? Light is made of tiny particles. And they said what light is these balls of stuff that go and hit things, and it's just, that's what light is. And this got changed in the early 1600s, well, by a few different people. And one of them was Isaac Newton, who said light isn't particles, it's rays, that it's just beams of light, literally, but it's rays that goes and hits stuff. Around the same time, a man named Huygens said that's not right either. Light, that what it is it's waves, and waves that goes and hits stuff. And it was in 1801, there was something called the Young's double slit experiment, which we're going to talk about the Young's double slit experiment directly in a few chapters. Not next chapter, but the chapter after, if I remember off the top of my head. But the Young's double slit experiment proved that light was a wave. Oh yeah, here we go. We're covering chapter 28. And said, look, proof, light is a wave. And just like we talked about last chapter, we have electromagnetic waves produced from moving particles. In 1801, they proved it. Well, they didn't prove it, but they had experiments that supported it. This eventually was followed by a mathematical description. This is known as the Maxwell equations. And in 1865, Maxwell, I was about to say Maxwell wrote four equations, but he didn't. Maxwell took a bunch of already made equations and put them together and proved that the four equations put together is what makes off light. These are all just electricity and magnetism equations, like Faraday's law and things like that. And it proved that light was a wave, that it's not a particle, it doesn't have mass, it's not moving. Light's just a wave. And that was kind of the end of the story, until for a little while. Because a little bit after that, and I didn't put the year here, which I put the year for everything else, so I should really put the year for this one, and I don't know it off the top of my head, but we'll cover the year for this next bit later on. When a man named Maxwell Planck came across some issues in physics in general. There's something called the ultraviolet catastrophe. I'm going to cover this in the story of Planck in chapter 30. So right now, just know there were some issues in the physics laws of physics we had, and in chapter 30, I'll do the details. But what Maxwell Planck said, hey, look, all this physics breaks down. If light was quantized, aka it can only exist in at set levels. And if the energy of light, follow this equation, NHF, well, N is a random integer, has to be an integer, 1 to whatever. H is what is called Planck's constant, which is written there, and F was the frequency of light. If that's true, all of the issues we had for light equations would go away. And people ask, like, well, why would this be true? And his response was, I have no idea why it would be true. But if it was true, the math all works. And then, like, yeah, some people there's a lot of scientists at the time had problems with that because they're like literally saying this thing we have no reason to believe it's true, but if it was, the math works is not a great way to prove things, except Sometimes it is, because if the math works, the math works. And so Planck suggested that light was not a wave, but was quantized. If it was quantized, that means it would have to be particles, that you could have one light particle or two light particles, but never a particle and a half. Now, as I said, we're going to talk about that a lot more in chapter 30. So I'm not doing more details now. Just know that that's the idea. Light is quantized, consists of particles. Actually, and he didn't necessarily, Planck didn't necessarily suggest particles. He just said it went by that equation, I should say. It was actually Einstein, and this is what Einstein got the Nobel Prize for, that said that yes, light is quantized. Planck is correct. And the reason why is that light is a particle, and that light was not a wave. This type of particle, a particle of light, was later called a photon, although the name photon did not come for, like I gave the year there, um, I can double check the years in between. Right now I'd have to minimize and open stuff up. But the name photon was coined pretty soon after Einstein's stuff. I think Einstein was like 1910, and I want to say Planck was like 1900, right on off the top of my head. And what Einstein says, if light is a particle, it explains something called the photoelectric effect, which we're going to cover in a later chapter. And what he said was light, each photon has an energy of hf. And Planck's equation, the NHF, is due to the fact you have an integer number of photons. And the energy of a photon is proportional to frequency. The higher energy something is, it means the shorter the wavelength. And this GIF on the bottom, I think, shows it real well. The blue has a low wavelength, but light travels at the same speed no matter which frequency or wavelength. It travels at c. And if something takes very small steps, if it's keeping up with someone with taking very big steps, you're going to have to move your legs really fast. And so light with a short wavelength taking small steps has to have a lot of energy to keep up with something that's taking large, slow steps. And so red light, which has a low frequency and a high wavelength, has the lowest energy visible. And violet light with a high frequency and low wavelength has lots of energy. And that's the idea. Light is actually a particle, not a wave. Which is a really dumb thing to say when I just spent an entire chapter saying, hey, light is a wave, last chapter. And this gets into the duality of light, or the dual nature of light. Light is neither a wave or a particle. Photons exist. Light is a particle. Light waves exist. The electromagnetic exists. Light is a wave. And the fact that light is a wave, that's how we can explain if light was not a wave, we couldn't explain things like polarization, diffraction, interference. And we're going to cover those in chapter 28. We also, if light wasn't a wave, couldn't explain everything we did last chapter about how light waves are made with electrons bouncing back and forth. However, if light is a wave, it cannot travel through space. And if light was a wave, we could not explain the photoelectric effect, which once again, I haven't explained yet. We're going to cover that in chapter 30. Fun fact about this traveling through space thing. Before people thought light could be a particle also, they thought space was filled with something called a luminous ether, and that all of space was filled with this goo, and that's what it made a wave in. The person who decided to test to prove the luminous ether existed is actually the test that proved light could be a particle. They went to prove one thing and accidentally proved something else. But either way, light follows the dual nature of light. It's not a particle and it's not a wave. It's not either one. It's its own thing. But we don't really have a macroscopic model to explain something that is both a particle and a wave. And so for the most part, what we do is we just say, instead of it's not really either one, we just say it's both. We say light is a wave whenever it needs to be a wave. Light is a wave to explain things like color, or like as in wavelength. It's a wave to explain how that's created, like we did last chapter. And light is a particle whenever it needs to be. And we'll actually just say interchange. Sometimes we'll do wave mechanics to explain light. Sometimes we do particle mechanics to explain light. We'll just do whichever one works at the time because they're both true. It gets a lot crazier, and as I said, we're going to cover this a lot more later. I feel funny covering it somewhat now, but the thing is I need a little bit of base knowledge before I can get into the detailed knowledge. But the general idea is light does whatever the fuck it wants. And if you do a test that will prove light is a particle, it'll do it. If you then do a test that proves light's a wave, it'll do it. It somehow is able to detect what you're trying to prove and match that and do it just like that. This causes a whole bunch of drama in physics, but as I said, we'll cover later. And actually, it is even worse than that because it ends up electrons also do this. And so that everything is also a wave and a particle, and that there is no such thing as a particle and there is no such thing as a wave. Everything is both. So that's fun. And that'll be chapter 30, so you can look forward to that. Any questions here so far?
No, not yet.
Good. As I said, right now I'm doing a general thing. We'll cover this in detail later on with shit Einstein said is kind of like should be the title of an entire chapter we do. But the reason I'm getting into this is we introduce light as a wave next chapter. And in this chapter, we are going to ignore light's wave-like properties. We are going to treat light as a particle for this chapter. And we're going to say, when you shine light on something, what you're doing is you are firing a beam of photons on it, at it. And that anytime, what's my laser pointer? That would be, sorry, I'm grabbing a laser pointer to shine on basically probably myself, but so when I shine this laser pointer on my hand, what I'm doing is I'm shooting photons out and it's hitting my hand. This is not going to be talking about the wave property. We're ignoring the wave properties for this chapter, but it's just boom, photons go, they travel in a straight line until they hit it. And what we'll say is photons or light rays, because basically what it is just a line of thing, that photons travel in a straight line unless it hits a boundary. That boundary could be of any kind. Could be, it hits my hand. That's a boundary. It could be it hits this shiny thing and bounces off. That's a boundary. Or it could be it hits a different medium, like a piece of glass. That's a boundary too. Sorry, there's a D missing there that I'm going to fix real fast so that sentence makes sense. And just because I noticed it, sure. And so light travels in a straight line unless it hits any material. And because of that, we're going to use what is called geometrical optics, also known as ray optics. That we're just going to say light's moving as a particle. And just like, basically, we're kind of going to say it's following Newton's first law. That light will travel at a set velocity, either speeding up or slowing down, and velocity is a vector, keep in mind, unless something acts on it. That unless it hits a thing, it'll move in a straight line until it does. Now, this is called geometrical optics because we're going to be doing a lot of geometry to explain it, but we're just going to say light travels in a straight line until it hits something. It's also called ray optics because we are going to draw light as a series of rays. And what we'll say is we'll just draw light as a vector and say if I shine my laser pointer like so at my hand, basically when I shine my laser pointer, light is shooting out of it. And that light shooting out of it is just going to go in a line until it hits something, a nice straight line. And we'll just draw light rays as a vector saying this is the way the light goes until it hits something, whether it of any kind. Okay? Now, if you are doing, and I would normally say ray optics, I seldom say geometrical optics, but if you're doing ray optics or geometrical optics, geometry, you're going to need to know a lot of geometry to solve geometric optics. I don't know how many of you have taken a straight up geometry class. It's not required for this class on purpose. So I am going to teach you a few geometry identities that you need to know to solve problems. This is separate from physics for ray physics. This has nothing to do with light, other than we're going to use it for light. This is stuff that is true in general. So, some quick rules. First off, if you ever have two crossing lines, opposing angles are the same. That if you have two straight lines, I can say angle alpha equals angle alpha, and angle beta equals angle beta. This will happen anytime you have two crossing lines. Also, related to this, and in fact, you can actually derive the second one from the first one if you want to go fancy. If you have two parallel lines and they are bisected by one, so I'm going to start with two parallel lines and then just add a guy across, I can also find similar angles. And how they phrase this is the alternate interior angles are the same. What I mean is basically is that this angle and this angle are the same. The two angles in between, but the swap from each other will always be the same. And if you use that combined with the last rule, if you have two parallel lines, parallel, separated by a line, that line could be at any angle. If I tell you any one of these angles, you can find all of the other angles. And I can do that because if I tell you this angle, if I tell you that angle, you then know this one, and this one. And we know that a straight line is 180 degrees. If I have this parallel line here, I can say, well, not parallel, it's just a straight line there. I can say that this entire bit is 180. If that entire bit is 180, I can solve for this guy, which means I can then know this one, and this one, and so on. Does that make sense? Last bit of geometry you need to know. If you have a triangle, the sum of the angles is 180. So that's the three things I want you to know. Moving past that, let's go back to light. What happens when light hits a boundary? Because I said light will travel in a nice straight line following ray optics until it hits something. And once it hits something, it's gonna do something else. When light hits an object, it can do three things. Honestly, when light hits an object, it normally does all three things. It's just a little bit of each. But we're gonna simplify and say when light hits an object, it does one of three things, and we're not gonna worry about ratios of them happening yet. The three things light can do when it hits an object. The first one is absorption. That light hits something, and it just heats the object up. This is heat by radiation, which we covered in Physics 1. That if you shine light on like a black shirt and the shirt gets hot, it's just absorbing the energy. This is because the energy of the wave follows that NHF equation that I introduced at the beginning of this chapter. And it can just absorb the light. Now, we aren't going to talk about absorption in this chapter. No, it's a thing that can happen. We covered it in Physics 1, though, so I'm not going to cover it more. Other than that, what light can do is if light hits off a solid surface, it can bounce like a mirror. And that if you shine light on something shiny, it bounces off of it, right? That if I shine light on this thermos, it bounces off and go flying around the room. However, if you shine light on something clear, and let me just check my video real fast. Yeah, I'll do this now. If you shine light on something clear, it can instead pass through and will bend. This is called refraction. That if I shine light, if I shine light on this glass block and have it at an angle, that the light will bend as it enters it. Now you can see the light is also reflecting off. There's reflection happening up here and refraction happening here. It can do both. Also, you see it bends as it enters the glass and it bends as it leaves the glass. It'll be anytime light changes a medium. Anytime light changes mediums, you'll have some reflection, some refraction, some absorption. That's not true. Anytime light hits any medium, you have some absorption, some reflection. If the object is clear, you will also have some refraction. right? When I shine light on this piece of metal, nothing refracts through at all. But we're going to just talk about normally just when we have only reflection or just when we have only refraction. Light bouncing off a surface or light going into a surface and bending. And we're going to start with reflection, mostly because it's the simple one. I'm going to be honest, all difficulties in this chapter isn't in the physics, it's in the geometry. So, when you shine light on a surface and it reflects, it'll always reflect one of two ways. There is what is called specular reflection and what is called diffuse reflection. And the general idea is when light reflects off a surface, there is a law to say what angle it comes in versus what angle it comes out. That's going to be on the next slide. If an object is perfectly smooth, if you shine parallel rays of light on a surface, and if something's perfectly smooth, all the light will bounce off the same. Nice, simple, organized. If an object is not smooth, all of the light rays that hit it will reflect off at slightly different angles. And it will look like this bottom right picture where you just see like a bright spot. This is kind of like, you know, when I shine this on my hand, there's kind of a glowing area around it. It's not just one spot, but a glow. That's because it's bouncing off diffuse over a rough surface. Just so you know, in this class, we are not going to talk about diffuse. We're only going to talk about specular. In general, diffuse follows the same laws as specular reflection, which I'm about to introduce. It's just you would need to know the exact structure of the material. It's not like, here's an equation for diffuse. It's like, if you want an equation for diffuse, figure out the exact angle every single piece of the surface is at a microscopic level, and then you can do diffuse. It's kind of a pain in the ass and near impossible. However, if light shines on an object that's going to reflect off of, we can measure the angle of incident, theta I, where the angle of incident is the angle the light hits the surface. And we are going to measure the angle of incident from the normal. AKA, if we have a mirror, and you know what? Let's get a mirror. If we have a mirror and light shines on it, like so, we are going to define the normal as perpendicular to the mirror. What I mean, I don't want that color, is we're going to say if the mirror is along this length, we're going to say the normal is perpendicular to that. And we will measure the angle from the normal. If I want to say, if I want to do this beam right here, if I want to say what angle that beam comes in, I will say this angle. You do not measure the angle between the mirror itself and the light, but the normal and the light. However, anytime light comes in at some instant angle, it'll bounce off at the same angle. This is called the law of reflection. That when light hits a mirror, the angle of incidence equals the angle of reflection. That whatever angle it comes in at, it's going to come out at that same angle. Theta I being incident, theta R being reflected. Oops. And going back to my little video here, which I'm just going to make smaller so I can show everything at once, is that if I have this light come in, when I start moving this mirror, I'm changing the incident angle. I know I'm moving the mirror, not the light, but I'm changing the incident angle because what I'm doing is I'm changing the angle between the normal and the light ray. And so whatever I bring in it, it's going to bounce out at the same angle. That, let's make this bigger so I can draw on it. That right here, my normal is this, and we can see, I'm just, you know what, hold on. I'll use the topmost beam, just since I have multiple beams. I can say the angle this comes in equals the angle it comes out. If I move this to a different angle, same thing. Ooh, I kind of missed. But the angle it comes in equals the angle it comes out, and so on. Okay? Now, solving problems in this are pretty straightforward because just incident equals reflection. How problems normally become complicated for this stuff is just, as I said, some crazy geometry. So I'm going to show you an example problem of the type that one might be asked to solve. So let's say I got this set up. I say light comes in and bounces off. Light comes in at a 65-degree angle at this mirror. And this mirror is at 120 degrees with another mirror. What is the angle that light leaves the second mirror? See, to solve these problems, it's just going to be a lot of geometry. And what I can say is that, and I got to be careful here, I'm going to match the symbols that they use in this, except apparently I didn't for the first one. But in general, I have to remember that the angle of incident equals the angle of reflection, which I don't know why I put it like that. It's a weird way for me to put it. Which means the angle incident equals angle reflection. There's the normal way. And so if I say this comes in at 65 degrees, I can say, and let me get my pen again, oops, that this one is also 65 degrees, right? Well, if that's 65 degrees, I can find this angle down here. Because this angle down here, that makes a 90-degree angle. So this angle reflected plus that angle must be 90. So that angle, 90 minus 65, must be 25 degrees. Okay, but we got a triangle here. And I know the sum of all angles in a triangle is 180. So I can look at this and say alpha plus phi plus 120 must be 180. Which 180 minus 120 is 60. Alpha plus phi must be 60. But I said phi was 25. So alpha must be a 35-degree angle. But look at this guy. That's another 90-degree angle there. And I know alpha plus beta must be 90. And therefore, since I know alpha, I can get the beta incident. But law of reflection again. Incident equals reflected. And so that must bounce out at 55 degrees. That's the kind of things you can solve with these. As I said, it's normally just geometry. But you can kind of just work your way through it. Does that make sense?
Yep, it does.
Okay. Writing a note that I need to italicize that beta. So let's do a different type of example. This one's kind of less of a workout example, as much as kind of an interesting fact. Let's say you got someone who's 1.8 meters tall, and they stand in front of a mirror, and they can exactly see their full height. The top of their head is right at the very top of what they can see in the mirror. The bottom of their feet is right at the very bottom they can see. Assuming that their eyes are 0.14 meters from the top of their head, which is a pretty reasonable assumption, from here to here. What's the height of the mirror? So, with doing these is often useful, like always, to draw a picture and label your points. So I'm going to say I have this setup. I have some mirror of height D, I don't know what it is, and I call the top of the mirror E and B respectively, mostly because I just stole this from a textbook and that's what they used. And I'm going to say that F is the top of their head, C is their eyes, D is the bottom of the mirror, and A is the bottom of their feet. I have no idea why they picked these letters, but I'm too lazy to make my own figure. What I can say is to see the bottom of their feet. That means light rays. When you see something, what happens is light rays are coming from that thing to you. If they can see the bottom feet in their mirror, that means the light rays are going from A to C off the mirror. But I know that the angle of incident equals the angle of refraction. That means the length from C to A, right, that height, must be equal to F of A minus F of C. Makes sense, right? That the height from his eyes to his feet is his total height minus the height from his head to his eyes. And therefore the distance from C to A must be 1.66 meters. But here's the thing. Because the angle of incident equals the angle of reflection, and I can do some geometry here to prove it, but what that means is the length from C to D must be half that length, because the angle is the same above and below. And so the bottom of the mirror must be 0.83 meters below his eyes. Because if it's 0.83 meters below his eyes, then it could bounce angle of reflection and see his feet. So let's figure out how high it has to go. I want the light to do this now. So the top of his head has light that's going to go hit the mirror, bounce, and hit the eyes. Well, the height from the top of his head to his eyes is 0.14 meters. But this uses the same logic, the law of angle of incident reflection, which means using the same logic, his mirror only has to go halfway up there. His mirror only has to be 0.07 meters above his eyes. And so to see your entire body, for this guy to see his entire body, let's say that, the mirror must start 0.7 meters above the eyes and end 0.83 meters below the eyes. But when you do that math, you get 0.9. And I said this guy was 1.8 meters tall. To see your entire body in a mirror, you only need a mirror half your height. Because if you have a mirror half your height, following the law of reflection, you'll be able to see your entire body. Okay?
Interesting. All right. Yeah.
Yeah. So that's everything with reflection. Reflection is simple. Light bounces. Yay. Angle of incident equals angle of reflection. So let's get into the more complicated setup that can happen. Which, sorry, I want to make sure I didn't skip a video real fast. Oops. Didn't mean that. I did not. Let's talk about the more interesting example, which is when light refracts instead. What happens when light hits a transparent medium? So you've probably seen, oops, didn't mean to do that. You've probably seen things before like this polar bear picture in the bottom, that when something's at the edge of a water, it'll look like the pieces are misplaced, that it looks like this polar bear lost its head, it's floating to the side. That's because you're looking through, some through water, some through air. And anytime light hits a transparent medium, some will reflect, which you can see in this figure here as the light going to 2, but some will refract, some will bend. Just like the video I showed earlier with my block here. That when light hits this block, it bends. And when light leaves this block, it bends again. What happens is just, the light goes at a different angle anytime you go through a transparent medium. Here you see it going from 1 to 3, and you see it going from 4 to 5. This is called refraction. And the reason refraction exists is because the speed of the wave changes. Now, this is interesting because I said we're only going to deal with light as a particle in this chapter. I forgot that I'm not going to do that right now. Because we're going to say refraction is basically doing light as a particle. It's going one way, bends, goes another. But the reason it does it is because of the wave nature of light. You see, I said last chapter that light travels at 3 times 10 to the 8th meters per second. But to be more exact, what I actually said was light travels at 3 times 10 to the 8th meters per second in a vacuum. The speed of light is only in a vacuum. In anything else, be it air or a piece of glass, light travels slower. And light will travel at some speed v. The reason for this is because when light hits a thing, its wavelength gets shortened. The frequency does not change, but it will go from a spread out wave to compressed and push shorter. And since the velocity of any wave is wavelength times frequency, that if we lessen the wavelength, we must lessen the speed. And as the speed gets slowed down, that will change. Well, yeah, the speed, as the wavelength changes, the speed changes. I mean, I can just leave it there. Now, for any given material, we can find what the speed of light is in that material. And to do this, we don't normally deal with the speeds. We normally talk about instead something called the index of refraction. Well, index of refraction is really by what ratio this light slowed down. The index of refraction, which uses the symbol n, is defined as the speed of light in a vacuum divided by the speed of light in that material. And that's it. Speed of light in a vacuum over speed of light in the material. Now, of note, it has no units because c is meters per second, v is meters per second. They cancel out. And we'll just use this value as a constant for any given material. It is of note, it does change slightly with temperature. The index of refraction of air at one temperature is not the same at another temperature. It changes for water and everything. But how it fluctuates with temperature is very minor. So we normally just say air close enough, just treat it at room temperature and keep it the same. But the index of refraction would talk about how much light bends. Also, keep in mind, light travels faster in a vacuum than it does not in a vacuum. And so n will always be greater than 1. So, to stress something, in a medium or in a vacuum, either one, F is the same. If you're in a vacuum, you're in air, F doesn't change. Assuming the color doesn't change, right? Like if I show you a red light, then a green light, F changes. But if I have a green light that's going from a vacuum into a medium, or from air into a medium, that if I take, when this use a laser. This laser has a set wavelength. I think it's 650 nanometers has a set frequency. I'm blanking on what the frequency is. But this light has a set frequency when it goes in. When it hits the water, its frequency does not change. Now, we often talk about what color is by wavelength. I know that light, my hand is covering it right now. I think it says 650, like my thumb is covering the writing. But this light, we can say, has a wavelength of 650. That 650 is only in the air. It is not 650 once it enters the water. And really, what we view as color is the frequency, not the wavelength. And we often will say there's a direct equivalent. I said there's a direct equivalent last chapter. That's because if you're not switching mediums. But what we can say is when it hits the water, its frequency does not change. What does change is its speed and wavelength. Now, being that n is c over v, if I plug in my c equations, I can find that I can also define the index of refraction as the wavelength in a vacuum over the wavelength in a medium. In general, though, you can find the index of refraction for any given material. Here's a bunch of them. One I want to stress is air. I did say that the, if we go from vacuum to air, there is an index of refraction change. Vacuum will be 1, right? It'll be C over C. Air's index of refraction is 1.000293. The index of refraction of air is so close to 1 that we're just going to treat it as 1. And we're just going to say the index of refraction of air is 1. Don't worry about what it really is. It will be fine. Okay?
All right.
Now, why this happens, I have a few different ways I can show it. I will be giving an example in a little bit, but let's real fast, I'm going to play a video that I think explains this well and is only 1.5 minutes long.
We all know that light bends when it travels through glass, water, or other transparent material. That's how a microscope, lighthouse, and spectacles all work. And you might even know that light bends because it travels slower through glass or water than through air. But why does light slow down? And how does it speed up again when it comes out on the other side? There's nothing there to give it a push. Well, if you think light is a wave, it's easy to explain. Electromagnetic waves simply travel slower through glass than through air. So the wave crests are closer to each other, but the light still oscillates the same number of times per second. It stays the same color. When the wave hits the air again, its color still doesn't change, while the crests spread out and it returns to light speed. The simplified explanation is that the energy of a wave is determined by its frequency or color, which doesn't change, so it doesn't need a boost to speed up at the other side. But wait, you say, I thought light traveled at the same speed in every reference frame. You still haven't explained how it can slow down. Well, now let's think about light as a particle. When light goes through glass, it gets knocked around and bumps into all sorts of molecules and electrons. So whenever it's traveling at the speed of light. But it's busy interacting with and scattering off lots of stuff along the way, and it doesn't necessarily take the shortest path through the glass. It's like the President of the United States trying to cross a room. If the room is empty, he can walk across directly. But if the room is full of people, all of whom want to shake the President's hand, even though he walks from person to person at full presidential speed, he'll get slowed down along the way. As soon as he reaches the far side of the room, though, he's free to resume his pace. Full speed ahead, Mr. President.
Yep, that's what I thought. That's done. And that's the general idea. Is that light, really the light is always traveling at the speed of light. It's just not in a straight line anymore because it's bouncing off things. So let's go for some derivations here though. Let's say light hits a surface and we can talk about what angle it comes in at, right? When it's in the substance one, which I'm going to, here my picture shows air to glass. So let's just say that. When it's in the air, V1 equals lambda 1F. When it's in the glass, V2 equals lambda 2F. If I divide one of those equations by the other, I get this, which says V1 over V2 equals lambda 1 over lambda 2. But we already said that N equals C over V. Rearranging, that means V equals C over N. So I can say C over N1 equals C over N2. With a little bit of rearranging, aka canceling out my C's, that becomes N2 over N1 equals lambda 1 over lambda 2. Which gives me this equation. N1 lambda 1 equals N2 lambda 2. And this tells us exactly how the light changes wavelength as it enters a material. But here's the thing. When it changes wavelength, it's going to cause it to bend. That's where we started this. Light bends when it hit a substance. And we can use this equation and a bit of geometry that honestly, I'm not going to get into the geometry involved with this because it's a little beyond what I feel like introducing just for the sake of a derivation, to derive what is called Snell's law. And Snell's law says when light hits a medium, N1 sine theta 1 equals N2 sine theta 2. That because of the wavelength change, the angle changes. And that assuming you measure your angle from the normal, just like we did before with the reflected, we can say that that's what happens when it hits a barrier. Now, the angle does not change in glass. The angle changes when we go from air to glass or glass to air. That in any given material, if the material isn't changing, your angle isn't changing. It's only when it switches. And going back to my video here, when I put this glass in, right now, theta is 0. Because my normal, if I want to find my normal is going to be perpendicular to the surface, which is right along this light. That means if my normal is 0 degrees, that means theta 1 equals 0. So N1 times 0 equals N2 sine theta 2. It comes out at the same angle if the light is parallel to the normal, because I have to get 0 equals 0. But if it hits at an angle, you are going to have a bending of light following Snell's law, that N1 sine theta 1 equals N2 sine theta 2. And this will happen when you enter the material and happen again as you leave the material. The same way that works with water, that when I change the angle it hits, so like I'm coming in somewhere between 40 and 45 degrees, it's going through the water between 30 and 35 degrees. That the angle changes following this equation of N1 sine theta 1 equals N2 sine theta 2. This is why things look bent when they go through water. Why this pencil looks disjointed, or the polar bear I showed earlier, is because we're just refracting off the surface of the water. And it's not refracting in the water itself. It's just as it hits the edge of the water, as it switches from water to air. Though in the picture of this pencil, it's refracting when it goes from water to air, water to glass, then refracting again when it goes from glass to air. Now, of note, if you pass through a block, like this guy here, this light refracts twice. Once when it enters the glass block, once when it leaves the glass block. In general, anytime, let me try to make everything fit here. Anytime you go from a material where its speed gets slowed down, aka a lower value of n to a larger value of n, the angle of refraction is less than the angle of incidence. It bends towards the normal. That if I was to go and draw my, draw my normal on this figure, my normal should be perpendicular to the surface. And actually, there we go. I got normal on both, on two different lines, but two lines that it passes through. I can say that this angle here is greater than that angle there, because I'm going from a lower value of n to a higher value of n. If instead you go from a high value of n to a low value of n, such as when I leave this glass, when I go from here to here, anytime you go to a lower value of n, your angle becomes bigger and you bend back out. Now, I've already explained why light slows down. That kind of makes sense, and I think that video helps with that. But just because light slows down, why does it bend is the next question. And I have been taught 5 million ways on why light bends when it does this. And most of them involve some really complicated geometry. But for I saw a physical science textbook with the simplest explanation for it, which makes full sense. And it treats it as an analogy. It says, let's say we have a mulching band. And this mulching band is a bunch of people mulching in unison. And they're all stepping at the same frequency. That they're just mulching along, set frequency, set rate, across nice ground. And as they're mulching, they start entering some mud. As they enter the mud, they're still going to mulch at the same frequency, but they're going to be forced to take a slightly smaller step. It's going to slow them down a little bit. But here's the thing. If they hit the mud straight on, so everyone hits the mud at the same time, it's going to get compacted, but they'll keep going. But if they hit that mud at an angle, my bagpipe player on the left, my bagpipe player on the left hits the mud earlier than my bagpipe player on the right. What that means is my bagpipe player on the left slows down earlier. That he slows down as he hits the mud, and the guys on the right slow down a little bit later after they hit the mud. They don't hit the mud at the same time. That means my bagpipe players on the right traveled faster longer. And because they traveled faster longer, that means they traveled a further distance. And if they traveled a further distance, if they're still going to move in unison, that means we pivoted. And that's what's going on, is because the light, that the side of the light ray, that if I have a ray of light, it's not just a single photon, you never have a single photon, but a beam of photons that's a few across, that some of them will slow down before the other ones. The light coming from A slows down before the light coming from B does. And this will cause everything to pivot. Now that is one way to explain it. The other one, which I like even better, is called the Fermat's principle of least time. This was proposed in 1662. And this was before we knew that refraction was because of wavelength change. And the thing is, this is also true. It works, but it involves some really weird jumps of logic. And what it says is light travels from point A to point B in whatever takes the least amount of time. That whatever way it can to get from A to B, whatever is fastest, light will always take. And that light somehow looks where it needs to go, does the calculations, picks the fastest route. Now, people didn't really like this explanation at the time because it means light is calculating how long it takes to get from point A to point B, which means light's intelligent, which is kind of troubling. So it doesn't really work. But if you go with this assumption, this can actually be used to figure out what path light will make. And what we'll say is that, okay, light travels at 3/4 of the speed in water than in air. If light didn't bend and had to go from the top of this box to the bottom of this box, I'm not looking at the angle, just saying top of the box to bottom of the box. If light didn't bend, it would take it longer to reach the bottom. Well, if it bends and does a more direct going down, it's going to get there faster. Because if it bends, then it's going to make less time in the water. It'll spend more time in the air, less time in the water, where it travels further. And actually, if you do this mathematically and say, what is the fastest way? It's going to match Snell's law, always. Also, if you do angle of incident, if you do reflection, this also works for reflection, which is kind of a crazy idea. Though very few people still bother the Fermat's principle of least time because it's just easier to say, hey, Snell's law. Now, I just realized I did go a minute over, so I apologize, but I will stop there. Any questions before I stop the recording?
Nope, and it's all right.
Thank you. Other than that, have a good day, and I'll continue this on Wednesday.
All right. Have a good day.
You too. See you.